Hi, today I'll talk about Taming the Zoo, the unified GraphIt compiler framework for novel architectures. This work wouldn't have been possible without the hard work from my collaborators at CSAIL MIT and University of Washington. In the recent years, we are seeing an explosion in the number of diverse architectures being designed to speed up applications. This includes general-purpose architectures like GPUs and CPUs, which can typically run applications from multiple domains. Every day, newer and newer generations and classes of these devices are being designed by different manufacturers. On the other hand, we have very specialized architectures being built to target applications from very specific domains like artificial intelligence. These specialized architectures are being designed by not a few, but hundreds of different manufacturers, each packaging their own special features. Similar specialized architectures are also being developed for other application domains like cryptography, physics simulations, tensor processing, etc. The application domains are also seeing a similar blow up in size. For example, GPUs were previously used only for accelerating rendering for games and animations. But today, GPUs also find use for accelerating video and picture editing, powering data science and machine learning applications, mining cryptocurrency and other blockchain-based smart contracts, running graph analytics, to name a few. Application writers also typically want to run one application on more than one architecture to best utilize all the fancy features being developed. For example, an application from a domain like video and picture editing could run on various architectures like different types of CPUs and GPUs, FPGAs, and ASICs. But the path from the application logic to the hardware implementation is not as straightforward. All these diverse architectures typically come with their own programming model, which are not only different from each other, but also are at various levels of abstraction. For example, specifically for video and picture editing applications, you would have to use CUDA for programming various generations and classes of NVIDIA GPUs. On the other hand, for programming AMD GPUs, one would have to use very different OpenCL programming API and libraries. For programming various CPUs, one would have to resort to writing high-performance C++, often mixed with low-level hardware-specific intrinsics. FPGAs and ASICs are programmed with a very different hardware description language, and the list goes on. This is same for other domains like AI and machine learning, where programming APIs like TensorFlow, PyTorch, low-level embedded C, or CUDA are used to program one or more hardware platforms. With hundreds of application domains being run on hundreds of different architectures, all exposing very different APIs, the problem of programming these applications is getting very hard. The result is that application developers are not able to get the best out of the hardware advancements without putting in considerable amount of efforts. But all is not lost. Language designers were faced with a similar challenge a few decades ago while trying to run single-threaded applications on diverse architectures. Each hardware had its own set of instructions and programming styles. But with a common and reasonably high-level abstraction like C and a modular compiler like LLVM, we were able to effectively program these architectures with reasonable effort. Not only this, because the compiler toolchain was modular, this abstraction was able to adapt to new targets by simply adding a new backend to the LLVM compiler. In this work, we will show how similar techniques can be applied to upcoming hardwares in a domain-specific way. Specifically, we will look at the graph analytics domain. Graph experts typically want to run their applications on various architectures like CPUs, GPUs, Swarm task-based parallel architecture, Hammerblade many cores to tune the implementations for the variations in the application and the irregularities in the graph inputs. Again, because these architectures come with very different programming APIs, they have to learn and use different libraries that are built specifically for their respective programming languages. This problem was partially solved with the introduction of the GraphIt domain-specific language and compiler by Zhang et al. In ISCA' 2018. This domain-specific language is substantially high-level, and the compiler is able to generate code for CPUs and NVIDIA GPUs. In today's presentation, we will show how we use the same abstraction to target very different architectures with the Unified GraphIt Compiler Framework, or UGC in short. The idea is simple. We start with a high-level graph language input, and we pass it through a specialized compiler that would generate C++, CUDA, Swarm C++, and Hammerblade C++ to run on the respective architectures. The compiler would also implement all the optimizations required to get the best performance on the respective hardwares. But generating code for the graph domain is hard. The right choices of optimizations depend not only in the variations on application logic, but also the graph input. We have different graph types like power law degree distribution graphs from social and web networks, and bounded degree large diameter graphs in road networks. Similarly, we see a lot of variations in algorithm types, like topology-driven algorithms like PageRank and data-driven algorithms like shortest path. Each of these variations require very different optimizations to be applied, presenting us with a very large optimization space with thousands of choices. The way we navigate this huge space is by splitting the input into two parts: the algorithm that specifies what to compute, and the schedule that specifies how to compute, that is, what transformations and optimizations to apply. The developers can then keep the same algorithm input and slightly modify the schedule input to generate a very different implementation from the compiler to better suit the generated code with the graph input. Another variations come from the fact that different architectures require very different optimizations. These optimizations are implemented inside the compiler as a series of analysis and transformation passes. For example, when generating code for CPUs, one has to choose the right implementation of the data structures, apply optimizations like cache blocking for better locality, perform data flow analysis to insert atomics in the right places, transform the code for direction optimized traversals, etc. The other target architectures, GPU, Swarm, and Hammerblade, similarly have their own set of optimizations. The result is that we will have to end up building four entirely different compilers, which is not scalable, especially when we would like to add new architectures in the future rapidly. The solution to this problem lies in the hardwares themselves. Let us look at these architectures and the features they offer carefully. Immediately, we can see that all the architectures have some notion of caches or cache paths. This means that all of them can benefit from cache blocking optimizations. All these architectures also have a large amount of parallelism available, which means load balancing the irregular graph computations will be critical for performance on all of them. What this means is that the compiler can share a set of common optimizations that benefit multiple architectures. Besides these, the graph domain also has common optimizations which are independent of the architecture, like push-pull traversals or several ordered processing transformations. This observation motivates a critical part of our design to separate the hardware-independent part of the compiler from the hardware-specific backends or the graph VMs. To create a common interface for all the graph VMs and to cleanly separate these phases, we also introduced a novel graph domain-specific intermediate representation, the graph IR, that captures all the details for correctness and optimizations. With this design and the optimizations we implement, we are able to speed up the code generated for GPUs, CPUs, Swarm, and Hammerblade by up to 52x, 42x, 5x, and 8x respectively. We are able to achieve all this with minimal new efforts per hardware. We will now get into the various parts of the Unified GraphIt compiler framework and see how they work together to get the best performance. But before we do that, let us understand the GraphIt DSL and the abstraction it provides. The GraphIt DSL is an imperative language with abstract data structures and operators. We have data structures like edge set and vertex set, which can be represented as different concrete implementations like CSR, COO, bitmap, boolmap, etc. We also have operators like edgeset.apply and vertexset.apply to apply a function on these data structures. These operators can have very different implementations based on the schedule, as we will see. We also have the user-defined functions which specify the actual computation that is performed on each edge or vertex. Finally, the programmer can add tags such as echelon shown here, which they can then reference in the scheduling language to configure various optimizations. The algorithm input, after being passed, goes through a series of analysis and transformation passes before final code generation. Because GraphIt takes the compiler approach, it is able to perform whole program analysis and transformations, which greatly expands the optimization space as compared to library approaches. If the programming model is clear, let us get into the first part of UGC, the hardware-independent compiler. As the name suggests, the hardware-independent compiler is a series of graph domain-specific passes running on the algorithm input parameterized by the scheduling input. Let us look at one such pass, the vector property analyzer. Here, I have a user-defined function from the PageRank application that is applied to each edge in the graph. The key component here is the sum reduction on the ranks in the destination of the edges. Now, for performance reason, we would want to parallelize applying these functions. But to ensure correctness, we would also have to use appropriate atomic synchronization primitives. Let us look at 3 different cases to see how this hardware-independent pass does this for us. For case 1, we will look at a push traversal, where we iterate over the outgoing edges of a vertex and push the values to the neighbor. We will also use a vertex-based traversal, which means that one source vertex is assigned to a single thread. By performing a data flow analysis, the hardware-independent compiler is able to determine that the ranks of the same vertex can be updated in parallel by multiple threads. As a result, it inserts atomic synchronization for correctness. In the second case, we will look at the pull traversal, where we iterate over the destinations and pull the values from the sources. In this case, the compiler is able to determine through the data flow analysis that multiple threads cannot write to the same value in parallel, and hence it doesn't insert atomics for performance. Finally, in the third case, we look at an edge-based traversal where the edges from a single vertex are mapped to multiple threads. Again, the pass inserts atomic here because it determines that multiple threads can update the same value in parallel. This pass is an example of a traditional compiler pass adapted to the graph domain, but is implemented in a hardware-independent way. The next part of UGC is the graph IR, which is the graph domain-specific intermediate representation. The main design goal behind the graph IR is to separate the hardware-independent passes from the hardware-dependent passes. We also want the graph IR to capture details for both correctness and optimizations. Here is a simple example of the graph IR generated for the BFS application. The graph IR nodes capture the features required for correctness with the means of arguments shown here in blue, and the features required for the optimizations with the extensible metadata shown here in green. More details about the graph IR are laid out in our paper. The final piece of the puzzle is the graph VMs or the graph virtual machines. A typical graph VM has three different parts: the hardware-specific analysis and transformations, the hardware-specific code generation, and the hardware runtime. But before we get into the implementation of the graph VMs and the optimizations we pack in them, let us carefully look at the features in our novel architectures and the optimizations they motivate. First up is the Swarm task-based parallel execution hardware introduced by Jeffrey et al. In Micro 2015. The Swarm hardware is similar to a typical CPU, except that it augments the CPU with a task unit for implementing fine-grained task-based parallelism. Swarm uses speculative execution ordered by user-supplied timestamps and hardware-managed data dependencies combined with hardware task queues to obtain order of magnitude more scalability than typical CPUs and GPUs. Because speculation is hurt by aborts caused by conflicting data dependencies, the main focus of UGC's graph VM is to generate code that eliminates as many false dependencies as possible. To see how that works, let us look at a part of the betweenness centrality application that runs the forward pass. On the left, we have shown the Graph DSL input for the application. We can see that a subset of the active vertices are stored in the vertex data structure frontier, and their edges are processed in each round to produce the next set of active vertices. This process is repeated till convergence. On the right, we have shown the default code generated from UGC without any optimizations applied. We can immediately see that the frontier data structure is read and written every iteration of the while loop. This creates data dependence, which hinders speculative execution across rounds. But we should be able to process new active vertices from the following rounds as they are being produced without having to wait for all the vertices from the current round to be finished. The graph VM performs a series of transformations to get rid of these false dependencies. Firstly, the graph VM performs a classic liveness analysis to identify that only one vertex set data structure is alive at any point in the while loop. With this knowledge, it replaces the output variable with the frontier variable. The transform code with just one vertex set is shown on the right. Now, the graph VM removes the entire while loop and replaces it with the bucket queue. The bucket queue interface allows scheduling of tasks with increasing priority. Each vertex to be processed is then mapped into the bucket queue with tasks that are to be performed on the vertices in the original frontier. Each task further enqueues the vertices for the next step to be performed on the frontier as shown in the highlighted code. The critical difference this makes is that now the vertices to be processed are never actually written to the memory. Instead, the operations to be performed on them are directly scheduled as swarm tasks. Now the vertices from different rounds can be processed out of order as expected. Finally, another transformation also splits the large tasks containing multiple reads and writes into finer tasks with fewer memory accesses and also inserts spatial hints based on the addresses accessed. This reduces the overhead of aborts and also gather updates to the memory location to the same file. This further reduces the number of conflicts. All these transformations together improve the scalability of the generated code. These passes are also configured by the options provided in the scheduling input to better suit the graph input and algorithmic patterns. Next up, we'll look at the Hammerblade Manicore architecture. The Hammerblade Manicore has hundreds or thousands of general-purpose cores, each with low-latency software-managed sketch parts. These cores are arranged in a 2D mesh and are connected with multiple high-bandwidth memory channels. The performance of the Hammerblade Manicore depends on how well the memory bandwidth is utilized in combination with the local sketch pads. To understand this, let us look at the PageRank application. Here, we have shown the user-defined function applied to each edge in the graph. There are two vertex arrays, new ranks and contributions. Each edge reads from the contribution from the source and updates the new rank at the destination. Let us look at a simple graph structure shown on the right. As the edges in this graph are processed, the threads random access into the vertex array new ranks. Typically, the number of vertices in the graph are large enough that the vertex data doesn't fit in the last level cache. As a result, many of the random accesses lead to a cache miss, reducing the effectiveness of the caches and hurts the memory bandwidth. To get around this, we partition the vertices in the graph and the edges incident upon them into two parts and assign them to a separate core. Each core brings up the vertex data of the vertices assigned to them into their core local sketchpad and only processes the subset of edges incident on those vertices. This greatly increases the reuse we can get from the sketchpad, improving our memory bandwidth utilization. For a typical graph where the vertex data is of size V, we partition the graph into V divided by V subgraphs, where V is the size of local sketchpads. The cores are assigned different subgraphs one after the other till all subgraphs are processed. This transformation is implemented in the GraphVM as a combination of code generation and runtime libraries. Finally, we will evaluate the generated code from UGC to see how well our optimizations perform. To study this, we will look at the four graph VMs targeting CPUs, GPUs, Swarm, and Hammerblade. We will compile 5 different applications: the breadth first search, single short sort as part with delta stepping, connected components, betweenness centrality, and PageRank. We choose 10 different graph inputs that cover power law and bounded decay distribution to account for variations in graph input. First, we look at how well the most optimized code performs against the default generated code without any optimizations. The heat map here shows the speedup of the most tuned schedule for a particular application over the default schedule in the 10 graph inputs. A number like 5.42 means the optimized code runs 5.42 times faster. We repeat the same experiment for 5 applications and the 4 graph VMs. We can see that we are able to get good speedups on CPUs for applications like BFS, which benefit from direction optimized traversals. On GPUs, we are able to accelerate power law distribution graphs because of our vast choices of load balancing strategies. The blocking optimization that we showed in the previous section is responsible for great speedups when running applications like PageRank on Hammerblade, and fine-grained task splitting boosts the performance on Swarm. Our paper has more detailed analysis of the results of each of the graph VMs, algorithms, and inputs. This evaluation mainly shows that UGC's framework is flexible enough that it allows implementing optimizations that can provide massive speedups. Next, we try to measure the scalability of our implementations. We run the best generated code from the Hammerblade and Swarm graph VMs with increasing number of tiles and cores and measure the relative speedup. We run these experiments on both road graphs and social graphs. Typically, it is difficult to obtain scalability on road graphs because of the limited amount of parallelism available in each ground. We are able to demonstrate good scalability, thus proving that we are able to best exploit the features in the hardware. Our paper has more evaluations comparing our implementations with the state-of-the-art and hand-optimized implementations. Finally, we also want to provide evidence for the fact that adding more graph VMs in the future would require very reasonable amount of effort. We count the number of lines of codes required to implement various parts of the hardware-independent compiler in the 4 graph VMs. The number in bold are the lines of code used by at least 2 graph VMs. Leaving aside the code generator and the runtime library, we can see that we are able to reuse at least 90% of the code base for more than 1 graph VM. With this, I will conclude the talk and summarize that the right domain-specific abstractions and compilers are a powerful way of programming and optimizing upcoming accelerators and general-purpose hardwares alike. We also showed that domain-specific IRs allow for decoupling hardware-dependent and hardware-independent optimizations while allowing maximum reuse. The Unified GraphIt compiler is available open source at the following URL. Please contact us if you're interested in learning more about our infrastructure or if you want to build a graph VM for your own architecture. Thank you.